Welcome back to this video tutorial, and this video is based on basic input-output operation. The data on which the instructions operate are not always stored in the main memory. The data need to be transferred between the processor and the outside world like this, keyboard, etc. The data are transferred between the memory of a computer and the outside world, which is known as input-output operations. The rate of data transfer from the keyboard to a computer is limited by the typing speed of a user, which is like some few characters per second, which is very slow in mode. The rate of output transfer from the computer to the display is much higher. That means a data transfer from the processor to the display screen, it can transfer some several thousands of characters per second, which is somewhat higher than that of an input data transfer. Okay, but the processor can execute many millions of instructions per second, so the processing speed is very high comparing to these two cases. Okay. So next topic is program controlled I/O. It is the way of reading character input from the keyboard and produces the character output on a display screen. Way of reading character input from the keyboard and produces character output on a display screen. The difference in speed between the processor and the I/O devices create the need for mechanism to synchronize the data transfer. So we have already seen that the data transfer speed of input devices is very slow and data transfer speed of output device somewhat higher, and the processing speed is very high. So we need some mechanism to synchronize this difference in data transfer speed. So here we have some solutions. On output, the processor sends the first character and then waits for a signal from the display that the character has been received. It then sends the second character and so on. First the processor sends a character to the display device in order to display that character. So after sending or after transferring the character, the processor waits to get a confirmation from the display device. Whenever the data is get available in the display side, it sends a confirmation to the processor which indicates that data is now available for display. Then it sends the second character to the display device. Okay. Input is sent from the keyboard in a similar way. The processor waits for a signal indicating that the character key has been struck and its code is available in some buffer register associated with the keyboard. Then the processor proceeds to read that code. Similarly, in case of input data transfer, the processor initially waits to get some notification from the input device indicating that a particular key has been struck by the user. Okay, when such a character value is struck by the user, it is stored in a register which is associated with the keyboard and then send a notification or a message to the processor indicating that a character is now available in the register associated with the keyboard. Then the processor start the data fetching from the input device to the processing side. Okay, after completing this data transfer, again the processor wait for getting the second notification which indicates that the second key is struck by the user. Okay, so this shows the processing unit, the keyboard and the display unit. All these units are separate and are connected or interconnected using a bus structure here. Okay, this keyboard, this is an input part and this keyboard is associated with a buffer we can call it as data in buffer, and also associated with this we have a status flag or a control flag, which we can call it as SIN. Similarly, associating with this output device, display device, we have a buffer, we can call it as the data out buffer, and also have a single bit of control flag information, we can call it as SOUT. Okay. So, striking a key stores the corresponding character code in the data in register of the keyboard to inform the processor that a valid character is now available in data in. The status control flag SIN is set to 1. A program monitors continuously onto this status SIN flag, and when this SIN is set to 1, the processor reads the content of data in. When the character is transferred to the processor, the SIN is automatically cleared to 0. If a second character is entered at the keyboard, SIN is again set to 1 and the process repeats. Look at this diagram. Whenever a user press a key on the keyboard, the data is stored into data in, and together with this action sets this status SIN flag value as 1. We have a monitor program which monitor the value of this SIN flag continuously, and whenever this value of this SIN status flag become 1, it informs the processor that a data is available now in this data in register of keyboard, so that the processor can fetch the value from this data in register. Whenever this data transfer between data in to this processor is completed, this SIN flag value automatically cleared to 0. So, and after that, whenever a new character is pressed in the keyboard, again this new value get loaded into this data in register. Together with this, the value of this SIN status flag automatically set to 1. The monitor program monitors the value of this SIN flag, and whenever this value of this SIN become 1, it informs the processor that this a new character now available in data in register, so that a data transfer start from this data in register to processor. Okay, after completing this data transfer, again this SIN flag value automatically cleared to 0. Okay, after transferring data from data into processor, automatically clear this SIN flag value to 0. Similarly, in case of outputting, we have a processor and a display. This display unit is associated with a register known as data out, and also have a single status flag information, we can call it as SOUT. Okay, when a characters are transferred from the processor to the display, a buffer register, data out, and the status control flag SOUT are used. Okay, for transferring data from processor to display unit, we need these two units like data out register and a status flag SOUT. When SOUT equals 1, the display is ready to receive a character. Whenever the value of this SOUT becomes 1, what's the meaning? Now this display unit is ready to receive a new character from the processor. And the program always monitors the value of this status SOUT flag, and this when this SOUT is set to 1, the processor transfers a character code to data out. The transfer of the character to data out clears the SOUT to 0. When the display device is ready to receive the second character, SOUT is again set to 1. Meaning, monitor program always monitors the value of this SOUT flag. Whenever this value of this SOUT become 1, what is the meaning? Now this display device is ready to receive a new character from the processing unit in order to display that value. So that processor transfer a new character to this data out register. So after completing this data transfer, this SOUT automatically cleared to 0. Whenever this data which is now available in this data out is displayed, again this SOUT value automatically set to 1. The monitored program again noticed this change, and whenever this value become 1, it informs the processor, and the processor transfer the next character to the display unit and store it in the data out register. So whenever this data transfer from processor to data out completed, this SOUT automatically changed to value 0. Okay, after displaying the value from this data out, after completing the display process, this SOUT value again set to 1, indicating that now this display unit is ready to receive a new character. Okay, so continue this process in order to display different characters. Okay, this indicate after completing the data transfer from processor to data out, this SOUT value automatically cleared to 0, and whenever this displaying the value from this register completed, again this SOUT value automatically set to 1, indicating that now this display unit is ready to receive a new character from the processor. After that, or after observing this change in SOUT, the processor can transfer the new value to data out register. The buffer registers data in and the data out, and the status flags SIN and SOUT are part of circuitry and are together known as device interface. Data in, data out registers and the status flags SIN and SOUT, all these units together called as device interface. So in order to perform the input-output transfers, we need machine instruction that can check the state of the status flags and transfer data between the processor and the input-output devices. The processor can monitor the keyboard status flag SIN and transfer a character from data in to register R1 by the following sequence of operations. Consider this one. If the SIN status flag value is 0, then the processor continue in a waiting stage. Whenever this SN value become 1, what is the meaning? Now a new value available in the data in register associated with the keyboard. So processor can read that value from the input device keyboard. That is the meaning of this. Meaning if the SIN value become 1. So if when this SIN value become 1, we can start a data transfer from the input device, that is from data into a register, processor register R1. Okay, if this SN value equal to 0, the processor continues in a waiting stage, and whenever this SN value become 1, the processor can transfer the data from data in register to the processor register R1. Okay, the processor monitors the status flag by executing a short wait loop and proceeds to transfer the input data when SIN is set to 1 as a result of a key being struck. After the input operation, reset SIN to 0. Similarly, in case of displaying, whenever this SOUT equal to 0, that means if SOUT equal to 0, the processor continue in a waiting state, and whenever this SOUT become 1, we can start a data transfer from a processor register R1 to the register data out, which is associated with display unit. The wait loop is executed repeatedly until the status flag SOUT is set to 1. If it is 0, the processor continue in a waiting state, and whenever this SOUT become 1, we can start the data transfer from processor register to data out. Okay. Whenever this SOUT set to 1 by display when it is free to receive a character. The output operation transfers a character from R1 to data to be displayed and it is clears automatically SOUT to 0. Okay, note this one point, memory mapped IO. Some memory address values are used to refer to peripheral device buffer registers. We can use some memory address values to represent input output registers like data in and data out. So that what is the benefit? We can use memory address values in order to refer this input output registers like data in and data out, so that we can use the same instructions in order to perform data transfer between input output devices, just like transferring data between processor and memory unit. Okay, so consider this one. The content of keyboard character buffer data in can be transferred to register R1 in the processor by the instruction move byte. Move byte data in comma R1. What is the meaning? Transfer data from data in register, which is an input register associated with the keyboard. So transfer data from this this data in register to processor register R1. Similarly, in case of displaying, move byte R1 comma data out. What is the meaning? Move content from processor register R1 to the output register data out. This is possible. That means we can make use the same move instruction in order to transfer data between processor and input output unit. This is possible if we can refer this input output register using certain memory address values. Okay. The status flag SIN and SOUT are automatically cleared when the buffer registers data in and data out are referenced respectively. Okay, if status flag SIN and SOUT equal to 1, that means data is available in data in register for the processor to read, and if SOUT equal to 1, what is the meaning? The display device is ready to receive a new character from the processor. After completing the data transfer, this register is automatically cleared to 0, indicating that it's not ready to transfer or receive a new character from the processor, or not ready to transfer a new character to processor. Some more modifications we have, that is, it is more common to include some SIN and SOUT in device status registers itself. No need to keep separate status bit information inside the keyboard and display unit. We can use certain bits present inside the device status registers in order to indicate the status value of SIN and SOUT. Okay, how it possible? Let us assume that bit B3 in registers INSTATUS and OUTSTATUS correspond to SIN and SOUT respectively. A single bit of INSTATUS register and OUTSTATUS register, which itself act as a SIN status flag and a SOUT status flag respectively. Consider this one. What's the meaning? Suppose here we have the INSTATUS and OUTSTATUS device registers, in which the third bit of INSTATUS acts as a SIN flag, and the third bit of OUTSTATUS register acts as a SOUT status flag, so that we can modify the machine instruction in order to support the data transfer between input device and processor, as well as the processor with output devices. Consider this machine instruction. Here we have test bit 3 comma INSTATUS, meaning test the content of third bit of INSTATUS register. If it is 0, the processor continues in a wait state, and if it is not 0, then perform a data transfer between data in register to R1. That means transfer data from data in register to a processor register R1. Here the third bit of INSTATUS register acts as the SIN flag value. If it is the third bit of this INSTATUS is 0 now, then the processor continues a waiting state, and whenever the third bit of INSTATUS become 1, what's the meaning? Now a new value is available in the data in register, so that we can transfer that value to a processor register R1 here. Similarly, here we have test bit 3, out status. What is the meaning? Check the third bit value of out status. This third bit of out status indicates the SOUT flag here. Okay, so check the value of that third bit of out status, which indicates the current status of SOUT flag. If it is 0, then the processor continue in a waiting state, and whenever the third bit value of this out status become 1, then we can perform a data transfer from a processor register R1 to the output register data out. Okay. The test bit instruction tests the state of one bit in the destination location, where the bit position to be tested is indicated by the first operand. Here it is 3. That means the third bit of out status indicate the SOUT status flag. If the bit tested is equal to 0, then the condition of the branch instruction is true. Okay, if the third bit value is 0 now, then the processor continues the wait state, and the branch is made to be beginning of the wait loop, so that the processor continues the wait state. When the device is ready, that means the bit tested become equal to 1. Whenever the third bit of this out status become 1, what is the meaning? The output device is ready to receive a new character, so that we can transfer data from register R1 to data out register. Okay. Thank you.